So today it's my great pleasure to introduce Loris, who's visiting us from the University of Wisconsin. He did his PhD with Rajiva Lohr at Penn a year and a half ago, something like that, finished up. So Loris and I went through grad school at roughly the same rate, saw each other at tons of conferences, and he works on an incredibly wide array of different topics. The recording.
Okay.
So, all sorts of interesting things about automata. CS Education, he built the Automata Tutor website. His projects on networking. You can also drive manual very well, and is an expert magician. So I'm ready to be amazed by this talk. Thanks a lot, Loris.
Thanks for the introduction. And so just disclaimer, I'm going to talk about automata, which is exactly one of the things I work on. And I do a lot of other stuff that I will tell you at the end. So this is going to be a fairly theoretical talk. So I'm going to have some slides at the beginning to make you believe it's practical. And then we will go into more crazy formal methods and stuff. But essentially, if you really don't like what I'm going to talk about, you just have to listen for this next 1 minute. And I'll tell you essentially, funky animation happened. So there was supposed to be automata here. It's going to appear at some point. I don't know why now. And the point is that automata are a foundational model for string and trees over finite alphabets. So people have been using them for quite a few years, probably more than 60 now. And they have great properties, and that's why people love them. And essentially, if somebody were to write a Yelp review about automata, would say, really cool model, recommended if you like finite alphabets. And so this talk is about symbolic automata, which is essentially a foundational model for lists and trees over arbitrary alphabets. And hopefully by the end of the talk, you will know what I mean by this. And they have the same great properties, even better in some sense. And they are a faster, more general, sexier algorithm. And the main thing that I like about them is that they have opened an opportunity for a completely new class of algorithms that people haven't thought about in the past. And if people were to write a Yelp reviews about symbolic automata, they would say something like this. So let's go into why you should care about this. But essentially, that was the whole gist of the talk. Symbolic automata, replace automata, throw your Sipser in the trash can, and start working from scratch. Sipser is a book about automata for those of you who's like otherwise. Don't throw actual Sipser in the trash can. It needs to work. So, okay, I'm going to talk about some motivation, why I started working on this stuff. So I wasn't just a crazy guy thinking about automata. And then what symbolic automata are. And then I'll show you two new algorithms that kind of came from this model. And we were like, whoa, incredible. And then other things I work on. So motivations. So motivation is called this section with subtitle, The Day I Try to Automatically Verify HTML Sanitizers. So what's an HTML sanitizer? So HTML sanitization is basically the task of avoiding that you do mean stuff with your HTML. And this is motivated by this non-existing anymore website, or existing but nobody using it, which is called MySpace, where people used to write comments. And MySpace was like, you know what, we are super cool. We're going to allow markup in our comments because we want our comments to look amazing. And people will write crazy stuff. And you could write almost something like this that would basically, whenever somebody opens your comments in the future, it would just trigger crazy stuff in their browser. So this is bad. You don't want to do that. So people wrote HTML sanitizers, which are these programs that they take the crazy HTML and turn it in less crazy HTML. And essentially, one say, OK, this is pretty easy. I can write one of these guys. I just go and remove script, and that's it. But it turns out that some people were very smart, and they would basically, for fun, try to break HTML sanitizers. And there was this famous worm called the Sami worm, which this guy found a super complex combination of CSS, internal, div-id. Like, it was just literally a crazy parsing mess. And he managed to break MySpace, and he did the world a favor, but still we don't want other website that we like to be broken. So we asked, OK, how do we verify a sanitizer? What would we care about a sanitizer? What do we want to verify in a sanitizer? So an interesting question would be like, does your sanitizer produce non-vulnerabilities? So we now have many websites. The type of attack is called a cross-site scripting attack. And there are plenty of websites that they show you like list and list and list of possible injections that you can do through cross-site scripting. So can we at least see that those cannot be produced by sanitizer? Does S produce HTML to start with, or does it produce something that can cause the parser to get clunky and produce unexpected behaviors? And is S defined on every possible HTML file? That's also an interesting one. It's like, or sometimes you just say, oh, I can't read this. And I'm not going to give you all the details, but essentially we ended up building this language called Fast, and don't focus too much on the syntax, but essentially this is an example of a fast program that you can actually run in your browser. I don't tell you the URL, otherwise you're going to start playing with it now. But essentially there is this language where you can write something like the remove script program that I showed you, the one that basically takes and removes the scripts from the HTML. You can write this other program that, let's say, escapes all the quotes. This is very important to do in sanitization because otherwise quotes can be used maliciously. And then you can, in fact, you can compose these two programs into a single one, like literally functional composition. But then you can also write things that relate to specifications. So for example, this is the set of bad outputs, that one that still contains a script somewhere in the tree. And then you can actually ask Fast to compute the good output, which are the trees that do not contain a script. And Fast can then type check this assertion. So let's look at what this assertion says. It says, is it true that for any HTML tree, my sanitizer produces a good output? So this is kind of just a hard three-post condition. And so you can actually ask Fast this property, and if everything is right, we will print that the assertion is true. Otherwise, something will go wrong, and here something went wrong. And Fast gave us a counterexample that was incorrectly sanitized. And if we go back to our program, we will see that there was an error here where we forgot to recursively invoke our program to remove scripts. So after we remove one script, we forgot to remove the remaining scripts. And this was essentially it's a possible mistake. People forget recursive invocation all the time. And if you run now Fast again, Fast will tell you, assertion is true. We know that you cannot produce a tree with a script anymore. So this was a toy example, but essentially this language is there and can do this type of analysis for you in actually a completely decidable fashion. It just restricts the type of programs you can write. But actually it turns out that you can write sanitizers, so it was a win-win because we were able to verify some properties of sanitizers. So that's old stuff. Let's move to the new stuff and what this work has brought us. So how does Fast work? So Fast is basically using this paradigm that it was essentially the core of my dissertation, which is essentially the notion of programming using automata. So we always thought of automata as kind of these crazy formal models that we learn because we have to, but actually they are computational model. They are, in fact, the simplest computational model, and there are many variants of them that are more and more interesting computational model. And essentially, what we saw in Fast is that we wanted to be able to do reasoning of this kind, so basically describe properties like bad output and complement them. So we want to be able to do things like complement. We want to be able to compose functions with themselves, and we want to be able to verify properties about these functions. So it turns out that a very good way to describe sets of inputs and sets of outputs is to use automata. So automata, I'm going to use very simple models for now, and then just tell you that it can be generalized, and we will go, later in the talk, we will see more crazy stuff. But essentially, automata are just this very elegant, simple model for describing sets of strings. So let's pretend for a second that our HTML sanitizer operates over strings. Well, automata essentially allows you to say, well, this automata accepts all the strings ending with the character B, and these are the things accepted by it. There was only one problem. Well, there's one good thing that automata have the property we care about. In this case, we can do complement with it, which is what we wanted. And we can also do things like intersection, and these are the operations that actually Fast uses under the hood to check all those properties I showed you. But they operate over what is called a finite alphabet. So this is like the first assumption when you take any class in formal languages is that you have a finite alphabet. And it turns out that if you want to verify real programs like an HTML sanitizer, you get trees of strings. So each node in your input is a string itself, and the set of strings is infinite. So you're already stuck, because let's assume it's not a tree. Let's pretend it's a list of strings. Still, each node in this list is a string itself. So you will need something fancy to reason about the string itself. And so basically, in general, we want structure infinite alphabets to be the elements of our input.
Sorry, this may not be a helpful question, but it's sort of the immediate devil's advocate argument, right? Which is, by adding a finite number of delimiters, I can represent a list of strings as a list of characters over a finite alphabet. Like, what goes wrong if I keep pushing sort of that approach?
Let me show the next slide first. I mean, here I show strings, so this is the easy case.
Yeah.
In general, we will want arbitrary data types or anything to literally, we can list of numbers, list of reals, list of whatever you want.
Okay, but nonetheless, I mean, at the end of the day, right, I can serialize over a finite alphabet.
Well, you might lose, in certain models, you change the expressiveness that you have by doing that. Because essentially, you're assuming that if everything is regular, everything goes well. But now we're going to also model what is called transformations. And based on how you represent your data, the class of things you can do changes. So if you want to do something like color this table blue and white if it has odd length, well, if the tree is unranked and you have all the children in the same place, you can measure odd even. But if the tree is serialized, you don't know if it's odd or even until you see the end of the tree. That's one case. But good question. So we want fancier alphabets. And here comes the model. So this is like the George Clooney of this movie. And so you have to admire him and look at him smiling. So essentially, symbolic finite automata, all there is to it is taking classic automata and making them modulo theory. So you like the word modulo theory. You probably know about SMT solvers, which operate modulo theory. So today is about automata modulo theory. And the idea is that it's the same as a classic automaton. It has a set of states, an initial state, a final state, and a set of final states, and the transition relation. But now the transition relation operates over elements that belongs to an input sort. So a sort is slightly different from an alphabet in the sense that it's a set of symbols together with a set of possible predicates you can write over those symbols. So in this case, we pick as our sort linear, integer, arithmetic. And in linear or Presburg arithmetic, or whatever you want to call it, and there we can write predicates of this form. We can say a number is even, a number is odd, and this symbolic finite automaton accepts all the list of integers ending with an odd number. And you might argue, well, you just took a model and completely changed it, because you basically put something crazy on it with like predicates. How is this, I mean, does this still work? So let's first look at, okay, as I say, we have this. And the other interesting point, as I say, we're talking modulo theory. So we're going to have actually some crazy interactions with SMT solvers, and these will all work together nicely. But let's look at first about how the automaton works. So it reads a sequence of numbers, because remember the sort is a domain together with predicates. So in this case, the domain is the integers. It reads a number. In this case, the number is odd. So we stay in this state. Now the number is even, we transition, and we keep moving like that. And the state is final, we accept. So the question is like, I took a model that was studied for 60 years, and now I changed it and made it strictly more expressive by basically allowing these crazy theories on top of it. And the question is like, do we have all this beauty still? And is it still useful? Because essentially that's the whole point of automata, is that they're useful because they have nice properties. And the answer is yes. It all still works. And I'll show you through the classic example of automata intersection, not only how this works, but how it works in a very nice way that gives us exactly the properties we want about this alphabet theory. So we have these two transitions of an automaton, of two automata, and we're trying to build their intersection. So the way you build automata intersection in the classic case is by doing what is called the product construction. So you have a state that says, let's pretend A1 is in P1 and A2 is in P2. What can they do next? To go to Q1, Q2. So what do you think it should go on the transition? Yes?
Logical conjunction of the two.
Exactly. So it's going to be the logical conjunction of these two predicates. So we're trying to synchronize them. So we're saying you can move if both of the transitions move. And this is already slightly different from classic automata, because here you would say, if this automaton moves with 4 and this guy moves with 4, then they both move with 4. But we can't do that now because the alphabet is infinite, so we have to do it through the logical end. And here comes the first question. Well, does our set of predicates contain that predicate? So we took the logical end of two predicates, but there are logics in which you cannot have conjunction. That's just not non-Boolean logic. And here comes essentially, this construction tells us exactly that we need something special about our alphabet theory, which is that it forms a Boolean algebra. Boolean algebra is a set of predicates closed under Boolean operations. And what in your head, you probably say, well, all theories have these properties. Turns out, no. For example, abstract domains, which you use every day, they only have union and intersection, but they don't have complement. So these are things that we take for given, but not necessary. In other cases, effectively propositional logic is a logic that is closed under Boolean operations, but it's not closed under complement. But we need all of this. Can anybody tell me how I check emptiness of that automaton? How do you check emptiness of a classic automaton? Anyone?
Reachability to the final state.
Reachability of the final state. How do you do it here? Reachability of a final state. But it's a bit of a different reachability. What if this predicate was, well, actually, what if this predicate it is what it is? This transition is false, is equivalent to false. And if we don't have a way to check whether the transition became false, we don't have a way to check reachability. So this is the other requirement that symbolic automata require, is that we need to be able to check satisfiability of the predicates in our algebra. And this is it. So if your alphabet theory forms a decidable Boolean algebra, life is good. And basically under this assumption, we redid all the classic automata theory and made it work for this more complex set of predicates. So already you can basically throw away classic automata and replace it with this. In fact, the finite alphabet just becomes a special case of this. It's the algebra of equality over a finite domain. That's all it is. And in fact, you have all these nice properties, emptiness, inclusion, whatever you want. So it's great. And so far, it's nothing too complicated. Like, people kind of saw this in the past, but they never thought too hard about it. And now today, I will tell you why you should think a bit harder about it. And one of the reasons is that this creates a very nice separation of concerns between the algorithms that you perform on the automata structure and the algorithms you perform on the alphabet theory. So this is why it's automata modulo theory, because now I can plug in any theory that satisfies these requirements and have for free an automata theory on top of it. So it's completely modular, and that's really cool. And then to make it work for fast, which is the language you saw, we also took another model called transducers, which are essentially automata that also produce output. And like this case is the automaton that doubles every letter. And we just turned also all of those symbolic, but that's not the topic for today. But you can also do this by basically allowing functions on top of predicates, and requiring closure under substitution is the only extra requirement you require. But the cool thing is that those transducers, they have also nice properties. So one of them is that they're closed under composition. So if you have a transducer T1 and a transducer T2, you can actually build a single transducer that describes the composition. And then you can use this property to do what is called pre-image computation. So if you have a set of output described as an automaton and a transducer, you can compute the set of inputs that produces that output. So it's like kind of backward reachability. And this is, I will show you, it's like really just using properties of automata. So I can define the identity transducer over bad output. So it's just like reads X, output X, but defined only on bad output. And then I can compose my program with it. So I get a new transducer that only outputs things in bad output. And the domain of the transducer is exactly what I want. So this is just automata operations. And now I can use this to actually do my type checking I wanted to do before. So how do I check this triple? I take the complement of the output. I take its pre-image. So these are all the inputs that produce a bad output. And then I just check that this doesn't intersect with the precondition. So basically, to check whether any of these inputs produces a good output, I just prove that none of these inputs produces a bad output. And this was all using these beautiful properties of automata. So this was what I've done. Like I've done a lot of these languages that can do this, and studied a lot of properties at the expressiveness level, and it all worked nicely. But then, and we built these languages essentially we use to verify a bunch of stuff. And this includes the crazy stuff. Like this sounds theoretical, but we verified this HTML sanitizer, some other complex programs that operate over list entries, some CSS rules, taggers for augmented reality. This one is insane. And even we verified animations of the Kinect skeleton. because the Kinect skeleton can be viewed as a tree automaton over the theory of coordinates, and really cool. So, and actually, it went the other way around. We wanted to verify these guys, and so that's why we developed the theory. But then we fell in love with the theory, and we started studying it. And one of the things that we stumble upon when working with these actual programs is that when you perform so many operations over automata, these guys get big. They get big to the point where essentially they are too large to reason about efficiently. And this was a problem because at some point, I mean, we wanted to verify bigger and bigger programs that were causing to create bigger and bigger automata, and then we would be stuck. So today, I mean, now I showed you that all of this is useful, so if you want, this can be the takeaway of the talk. But today I will show you two techniques that then basically spawned from this necessity for basically handling large inputs. And the two techniques are, one is keep them small, so minimization, and the other one is when you can't keep them small, avoid building them at all. Can you actually check operations over many automata by avoiding combining them into a single one? And from now on, it will be technical, so feel free to stop me. So are there questions before I start with this one? Yes?
Maybe I'm jumping the gun and asking this question, but there was already a way to minimize regular deterministic finite automata.
Yeah.
And we saw how we can take the intersection algorithm for those and translate it very naturally into the symbolic automata. So why doesn't that?
It works, and I'll show you it works very easily, but then I'll show you it doesn't work. Like it doesn't scale. So there is always this issue, like all the algorithms, I will show you actually a hammer that hits all the symbolic automata algorithm and reduces to the classic case, but in a very inefficient way. And that actually will highlight one of the weaknesses of original automata. So this is two papers. So one is this Popple 14 paper on minimizing just symbolic automata, and then in the last leaks, we show actually a way to do this for tree automata, and that one would be really cool, because that one is really like, when we saw it, it was like, can't be. I mean, this is not possible. This works. And it works. OK, so what is this? I'm going to talk about what is minimization, show the classic algorithms, as your colleague said, and then show the new symbolic algorithm that really uses the structure of symbolic automata. And finally, I will show you the leaked work on how we can reduce minimization of tree automata to minimization of string automata for free, because just we have symbolic alphabets. So what is automata minimization? Is taking a mess and turning it into something more readable, preserving the language. So you want to take an automaton that is really big and trying to make it as small as possible. And the trick in minimization is that it's based on a very beautiful theory called Myhill-Nerode equivalence classes, beyond the scope of this talk. But the whole idea is that in an automaton, there are some states that they do the same thing. And if you find the states that they do the same thing, you can just merge them together into a single state. And if you repeat these until you find the minimal automaton. So I'm going to call distinguishable two states that are inequivalent. So they can be distinguished. And the notion of distinguishable is very simple. It says if you have two states P and Q, I can distinguish them if I can prove to you that they're different. And the proof is a string on which one goes to a final state and the other one goes to a non-final state. So that's a proof because I show you that they go to different places. So they have different languages. And this is it. And the beautiful thing is that this by itself gives you an algorithm for minimizing automata. And Moore saw this a long time ago and say like, oh, well, if I know that two states are distinguishable, and I find other two states that with the same symbol go here, those two states are also distinguishable because there exists a W here, there exists a W here. Now I have a W, which is a witness for those two states. So this is super easy, like fun, like that. And the algorithm is essentially just start with all the final states are distinguishable from non-final states, and then until you reach a fixed point, do this trick and add more pairs. And when you're done, you found all the states that are distinguishable. Those that are not distinguishable must be the same, and you're done. And actually, turning this into symbolic algorithm was also fairly simple. It essentially is the same story. The only thing that you change is that if two things are distinguishable, and I find two guards that go into it, and their intersection is satisfiable, I also have a witness to distinguish these guys. So here comes the first interesting bit of symbolic automata. So you will observe that in in this shot, I didn't have to iterate over all the symbols to find one that gave me the distinguishing factor. I just had to find two sets of symbols that they overlapped. So this already shows you, like, I'm basically doing things symbolically and avoiding iterating over all the symbols. I only iterate over the ones that matter. And we will go back to this. And I can change the algorithm, very simple. I just put this SAT query at the end of the check. The problem, and this was already observed for classic automata, is that Moore algorithm is quadratic. And this was, we were using this for an application inside Microsoft where we were trying to do random password generation for, basically you give me a bunch of constraints, like it needs to be at least 10 characters long, contain 3 letters, one number, one smiley face, whatever you want. And then we generate a password at random for you so that you don't have to come up with one. And this can be done by automata intersections, and then you just generate a random string in the automaton. But the problem is that, like, minimization was not scaling, because these automata that you use for passwords are very ugly. They have something like, oh, the password has to be between 3 and 3,000 characters long. And the automaton for that is 3,000 states. And when you combine it with all these checks, things get nasty. And they wanted it was at 18 seconds for 15 characters long, and they needed it for 128 characters. So this was not going to happen. So we went in the literature and looked at what people have done for finite automata. And it turns out that Hopcroft observed this a long time ago, in 1972, I believe, and came up with a very beautiful way to avoid the n square. So the n square before was given by the fact that I was considering all pairs of states, essentially. And now Hopcroft says, like, you know what? I think we are redoing some work here. I like the idea of starting that final and non-final states are distinguishable. But before, what we were doing, we were adding things that are distinguishable kind of one at a time. Here instead is like, let's reason about what partitions of the states have I proved to be distinguishable so far. And then he says, okay, let's start. I have these two guys are distinguishable. So everything in this bucket I know is different from everything in this bucket. So what can I do next? Well, I can take anything in B, which is the blue circle, and take his pre-image on some symbol. So now I found a bunch of states that when reading A go into B. So these are all the states that when reading A go into B. And you see that, like, similar to what we did for Moore, everything that is in this circle is distinguishable from everything that is not in this circle. Right? It's the same as before. I found the symbol on which I go to distinguishable places. And so I can split kind of all these things in one shot. And this will be still n square until we observe the following. So let's say I keep doing this until I iterated over all the symbols. OK? So I've done this for every symbol in the alphabet. So by the time I'm done, I split everything according to B, and I'm done with B. I will never look at B again. But what can happen is that while I was splitting for B, I cut B itself in half, because something within B was distinguishable with respect to B. So now the question is, do I need to split with respect to both P1 and P2? Yes or no? And Hopcroft, at this genius moment, will say, no, you don't. And this is the reason. So I'm done splitting with respect to B. So let's take any other set in my partition. There are 3 possibilities. On every symbol, this guy does not go into B. Because if some go into B and some do not go into B, it means I wasn't done splitting with respect to B. So this is one possibility. Nobody goes to B. Possibility number 2 is they all go to B, but they fall into the same bucket. In which case, it doesn't matter which one of these 2 I keep. They will give me the same result. Case number 3, some of them go up and some of them go down. It doesn't matter which one I keep. I will still produce that split. So basically, he observed that, like, when you're done with one set and you cut it into half, you only need to consider one of the 2 halves. And which one do you pick? The smallest one, of course. And this basically shows that you can do it in n log n. And basically, Hopcroft algorithm is, you don't have to understand the algorithm, but the whole point is that the complexity is size of the alphabet, because you have to iterate over all the symbols, times n log n. Let's do it symbolically. One problem. this was one of the cases in which basically going to symbolic setting was a mess. Because in 40, 50 years of automata theory, people have always looked at this alphabet as a small thing that you can iterate over. Yes?
Is n the size of the number of transitions or
States.
the number of states?
States.
Okay, states.
Kn is the number of transitions.
Okay.
Because, yeah.
Sorry, well, and maybe this is where you're going, but yes, I have an infinite alphabet, but for any particular automata, I have the set of formulas. Okay.
You're one slide ahead. Okay. Okay, so basically this is, I can't iterate over the alphabet because it's infinite. As it then says, we only have finitely many formulas in each symbolic automaton. And these finitely many formulas induce a partition of my alphabet, which is finite. Like, any of these regions cannot be cut further using just these predicates. Beautiful. We just found an algorithm. So symbolic automata are garbage because you can take these all regions, create a new finite alphabet, and pretend you are a normal automaton. So each of those regions is separate. Like it's like a finite alphabet. That would be great. These are called the minterms. Yeah, they're basically the set of all satisfiable Boolean combinations of a certain set of predicates. There is only one problem. Well, there are many problems. So we can basically do Hopcroft where we iterate over the minterms, but ta-da! There are exponentially many minterms in the size of the predicates. Not only so, if each predicate in your original automaton has a size k, each minterm has size n times k, where n is the number of predicates. So you generate these giant predicates that are like phi1, n phi2, n not phi3, n phi4, and not like each of them has this form. And basically, you lose before starting. And in fact, I will show you cases in which this can happen. And you don't want to do that. If you can avoid it, you don't want to do that. There is always a worst case in which that might happen, but you don't want to do it if you can avoid it. And for certain algorithms, you can show that you can avoid it. So this was basically the point in which we saw that something cool was happening with symbolic automata. So essentially, the worst case of the minterms is the alphabet is actually the alphabet of finite automata in the finite case. But the minterms were basically capturing how much information the automaton can convey. So if an automaton has n states, it can only have n squared transitions after you treat it as a symbolic automaton, regardless of the alphabet. Because any transition between the same states, you can just take their union and pretend it's a single symbol. So basically here something was happening where people have always thought of the alphabet as something special, but actually you soon hit the case in which certain symbols are indistinguishable, and the minterm was characterizing that. And so we went and tried to think, how do you do Hopcroft algorithm without building the minterms? And this hit us, and like when we submitted this to Pop, I got like the best review I ever got for a paper. I mean, humble brag, but there was like, I didn't even know I did something useful. And then this guy was like, whoa, if it wasn't for symbolic automata, we would have never discovered this algorithm. And that was true, because in hindsight, it's obvious when you look at it for symbolic automata, but you will see that in the finite case, you wouldn't have seen it. And the algorithm is this. So if you understood Hopcroft, this is going to be like, of course, duh. So we have our B, we are trying to partition with respect to. And before what we were doing, we were taking a symbol and take its pre-image. So essentially, the formula was like, there exists a symbol A such that there are two states that one with A goes to B and one with A doesn't go to B. But when you have two existential quantifiers, you all know that you can swap them. So instead of looking for a symbol and then for the states, we can first look for two states such that we pick all the symbols that they used to go to B. And now we have two cases. The most interesting one being, if these two sets are different, it means that there is a symbol on which one of them goes somewhere else. So now we turn that search over all symbols to find the distinguishing factor into a satisfiability query of checking whether these two guys are the same. And this was like why didn't we see this before? And it's like it's so simple when you look at it, but it was actually, if you think over the finite alphabet, this doesn't buy you anything. because there was no notion of efficiently searching the alphabet. But when you have this partition into, when you actually treat it as predicates, you have this beautiful set semantics that we can think easily about and found it. And in fact, this also works better in the case of finite alphabets, and I'll show you soon. And basically, you can do this partition, and you're done.
Is a way to think about this that the generating exponential minterms is like this super eager thing where you're not going to need most of them because you only have so many states and so many formulas, and so generating every minterm is just it finitizes, but in like the most inefficient possible way.
Yes. So essentially, the point is that like if you have n predicates, there will be only n square. So for the minimization, so basically this raises a new question for symbolic automata. What's really the complexity of these operations? And in this case, it's like you only need n square satisfiability checks in the worst case, like every pair of predicates, versus before it was like 2 to the n.
Yeah, it's almost, I mean, probably another equivalent way of saying is I have these n squared formulas, n states, and most n squared formulas. Do not write down the full truth table.
Yeah, that's essentially it. Yeah. It's just like the distinguishability doesn't come from the predicates, come from how the automaton uses them. And in fact, actually, there is another cool factor. Actually, this doesn't require full Boolean algebra. You can do this trick just with the intersection and union. You don't need complement. But like this basically raised a bunch of questions of like, have we thought the wrong way about this alphabet the whole time? And all these algorithms, you see, they have this k factor of complexity. And it turns out that k that didn't mean anything. It's not a property of the alphabet. It's a property of the automaton most of the times. And let me show you a quick example of how this works. So you have these two states, and you're trying to distinguish with respect to this b. So you take the two states in here, and you look at their transitions going to b. And you have x greater or equal than 2 and x greater or equal than 5. And now you ask, are these two predicates equivalent? Do they describe the same sets? The answer is no. And so you can split this. And this is how it works. And the equivalent of doing backwards would have been, oh, can you take a symbol that crosses these transitions and there's two different states? This was just like the wrong way to think about it. And of course, the question is like, did it work? You know, all this BS about telling us how fancy symbolic automata are. And I'll show you actually that this is like, it was a game changer. So this is a benchmark of 1 million something automata, no, 5 billion automata. In case you haven't, if you ever run out of automata, you can ask these guys. And so they actually, this guy's dissertation was to generate random automata so that you have guarantees on actually almost all the automata being there. And they basically have, this is like for 10 states, 20 states, 15, 100, and the x-axis is the number of symbols in the alphabet. And we implemented all the algorithms to see how they worked. So Hopcroft is Hopcroft algorithm with the minterms. Moore is Moore algorithm, and new is the new one. And you see that the new algorithm, I mean, here is noise. Like these are so small automata that you can't even see, but otherwise it's consistently faster than all the other algorithms, even on these very cases where the alphabet is so small that it shouldn't matter. And this is another interesting case. We took 3,000 regular expressions from regexlib.com. So this is like a crowdsourcing website for regular expressions where people go and say, oh, I need a regular expression to match against the Canadian phone numbers. And they're like, OK, and people write one, and then they use it. And we took them, build the automaton, and try to minimize it. And you can see, so this is the new algorithm. This is Moore, and this is Hopcroft, or one of the two. So this is Moore, and this is Hopcroft. And you see how Moore eventually gets the quadratic problem. Like with more states, Moore becomes low. Hopcroft starts a bit bad because it has this iteration over the alphabet, which is overhead, but eventually keeps the n log n. So the axis here, I think, is in log scale. But look, we are orders of magnitude below with the new algorithm. It's just like there was an overhead in how many queries you were doing to the alphabet. And this eventually comes up.
Sorry.
Yeah.
What regular expression had 10,000 states?
Oh, these are the determinized ones, because you have to determinize and minimize. Also, a very easy one. The length is between 1 and 10,000.
Yeah.
People, okay, like there is this issue, like, I mean, we know this as programming language people. It's like there is this tendency for people to put feature in a language, say nobody's going to use them. And you know how that ends. And with regular expressions, people are like, oh, I can describe all the tables that are between 1 by 100 and 1 by 100 using a regular expression that says, is the row 1 by 100 within a 1 by 100? and it goes insane, because then you get 10,000 states. It's like just, so The lesson learned is don't give people choice when it comes to language. or make them believe there is a choice, but don't give it. So, okay. So this case is a case we are artificially built. Actually, I will show you later. It's not so artificial, in which we basically say the first bit is 0. So this is an alphabet of bit vectors. And you say the first bit is 0, the first bit is 1, the first bit is and so on. And these other ones say the first bit is 1 and then the same. And the minimal automaton just collapses these two. But when you take the set of Boolean satisfiable combinations of these guys, you get basically exponentially many predicates, because you get all the possible bit vectors. And this Hopcroft reflects it. Interestingly, Brix, which is the automata library of choice out there in the wild, does the same problem. Was built in the midterm. So other library was doing something symbolically, kind of. But you see that like the only easy solution there was to build these minterms, and these people fell for it. In fact, in this case, even Moore does better, because Moore doesn't build the minterm. But the other algorithm, bang, below 1 milliseconds all the time. And this is like for up to predicates of size 2 to the 20. I mean, set of alphabet set of with the alphabet of size 2 to the 20. So pretty cool.
Well, this is, I mean, I love this stuff. This is awesome. But this is sort of like the case where you're guaranteed to do the best.
Yeah, but like
and it's a funny thing on like minimization is a funny thing in this context because I can move the conjuncts into the formulas and collapse this down to 4 states or whatever, right? Which is something you're not considering. So why can't I put get rid of P1 and have the arrow from Q0 to P2 be not beta not and
oh, well, you can't do that because you're reading 2 symbols. Then you change the model to reading 2 instead of 1.
I got that. Okay.
And actually, we have a model for that, and everything breaks down.
Okay. I agree on that point. So I go back to, yes, this is the skeleton of where you're going to do it exponentially better.
Yeah. I mean, this is pathological, but I'll show you actually on fast programs that was happening.
Oh, right. So I believe that this sort of subgraph, if you will, would arise in practice, and it is the subgraph where you will most shine.
So the other case was this one. So we randomly generated a bunch of programs in fast that were operating over a complex theory. So here the alphabet was pairs of strings and integers. So something pretty messed up. So it was actually an automaton of automata. I'm really proud of that. And here actually, when you randomly generate predicates, you get these very weird ones that cause midterm generation, essentially. And Hopcroft was dying again. And look again, this guy, bang, flat at 0. Like it's essentially, the complexity of the predicates doesn't change. And that was really the beauty here of understanding that part, that just like you need to combine things in a smart way and not in a silly way. And so I guess we had a lot of questions. There are other questions, otherwise I will show you really the moment where I was like, wow, this is cool. I mean, this was cool. This is going to be cooler. Now questions? Okay, let's go into the cooler stuff. Okay, so fast is a language for tree transformation and list transformation, but it also handles trees. And to handle tree, you need what are called tree automata. So tree automata are exactly like string automata. I'll show you immediately the symbolic ones. So you have a predicate over a node. And so in a string automaton, you say, if I reach the previous symbol in state Q, then I move to state Q1, right? So in a tree, you don't have a previous symbols, you have children. So if you say, if the left child, I reach it with Q1, and the right child with Q2, and the node is labeled with phi, I move to Q. So essentially, visually, it's like I'm processing bottom up. I reach these 2 trees with these states. Now I see an A, such that the A is a model of phi, and I just move my state 1 up. And I keep going until I hit the root. And let me show you an example. So this is an automaton that checks that all the left children are positive numbers. Yes, are numbers greater than 0. So it just says, oh, if the number I'm reading is positive and his left child was positive, I don't care about the right child. I just say it's going to be positive. And you can run it on this automaton. So for example, you can start, these are the leaf rules, the one without children. It says, for a number greater than 0, say positive. For a number smaller or equal than 0, say state negative. And you can do this here. They were all positive, so we just put every Q greater. And then you can say, you can apply this rule that says, if they're both Q greater and the number I'm reading is smaller or equal than 0, go to Q smaller or equal. And then there's going to be a similar rule, and then eventually we infer this, and we succeeded in saying that this language has the property we wanted because Q greater is a final state. Okay, so this is going to be a bit faster than the level of detail I had before. But the point is that there is a very similar notion of distinguishability for these guys, which is essentially the two states P and Q are distinguishable. Instead of being a string, the witness for distinguishability is a context tree. So a context tree is a big tree that has a hole. And P and Q are distinguishable if a tree that can be read using P and a tree that can be read using Q, so a tree that when processing gives me P and Q, if I plug them in here, the overall tree, one is accept, one is reject. So it's kind of the same notion. You can think of this as being a string in some sense. It's like the context is like what's left to read of the tree from that hole. And actually, that's the way you should think about it. That essentially this context is the suffix of the string left. And this was the point where it hit us. Trees are strings when it comes to minimization. And essentially, we gave first a Moore style algorithm, but then we really saw that like it was really just a string. And this is the intuition. So bear with me for like 56 seconds. So this is a rule of a tree automaton. You can view it like this. So there is something that I process bottom up, reaching P1, P2, and I move to P. And there is some predicate phi in here. So this, if I view it as a string, how many contexts can send me to this point? Well, context number one is the one in which I arrive with P1 and I didn't care about P2. And context number two is in which I arrive with P2 and didn't care about P1. So I create this new alphabet for strings that says, if you are in P1, so I'm here, and the other guy arrived with P2 when reading phi, so the whole is the context. So basically, this says, I was here in the context. I'm pretending to be this context. Then you can move to P. And I will have a similar rule to mimic the other context. So I'm kind of doing both the context in one shot. And for every rule, there are at most, in this case, 2, but in the worst case, there are like n number of states context. So you will have to believe me a bit because the proof is a bit involved, but actually it all works out. If you minimize this automaton, so this automaton operates over a different alphabet theory. So it's a theory of tuples, where the left child is the original Boolean algebra, and the right child is a new Boolean algebra, which is fine, it's all finite and works. And it turns out that the product of the Boolean algebras is also a Boolean algebra. So you can actually minimize this automaton using what we saw now. And if you do that, and use the classes of states that you got, you actually get the minimal tree automaton as well. So this is like, there was no way to see this with finite alphabets. It's just like, it was a lifted alphabet. It was like, or maybe there was a way to see it, but actually it wouldn't have worked because it turns out that the alphabet you built here has exponentially many elements at least, because the number of combinations, so if you have a tree of arity n and you have n states, you have q to the n possible ways to combine those tuples. So it just wouldn't have worked. And here actually, by just using what I showed you up to now, it all worked out. And in fact, we did more experiments, but this was the interesting one on fast programs, where it kind of, in some cases, it beat the classical algorithm, because we could use the n log n factors that you cannot use in classic tree automata. And this is like lots of transitions, like these are big automata. But the whole point, it was just like, using symbolic automata, you could model this complex idea of the context. Yes?
Why the spike around 60,000?
So these are few cases. I think these are literally 3 examples here. So this is most of the volume. It was very hard to generate examples that we could determinize for this size, because we generate them at random and then the determinization produces stuff. But this is essentially just one case that was really big and it went bad. And this is one case that was even bigger and it went well. Okay. And the point is that at this point it gets very hard to predict because we are doing a switch of Boolean algebra. So who knows what happens. But the reduction uses tuples in C3, which are not exactly easy to predict what they do, like actually data types. So, but the cool thing is that we had a new algorithm for minimizing tree automata with 15 lines of code by just reducing to the string automata case. symbolic. So, problem. Even the smallest automaton can be large. So this is the example that Dan said, oh, it seems like the prototypical bad example. Turns out that like people that write, sometimes, basically what I showed you was something that could check whether the ith bit is 1. So this is the automaton that checks whether some element in the input has ith bit set to 1. And you can have the intersection of these automata. So I want one that checks whether the first bit is 1, the second bit is 1. So the intersection of this automata has exponential size. It's basically all the possible symbols. And this seems artificial, but it's actually equivalent to the LTL formula, eventually A1, eventually A2, and eventually A3, and eventually A4. So this is none. Like the automaton for this formula is bad. So even if you minimize it, you're going to get back what you started with. So life is not very good. And the problem is that sometimes you don't really need to build the automaton. At least there is the hope that you don't need to build the automaton when you want to check for simple properties like subsumption, equivalence, or emptiness. You might be able to do it without actually building the automaton. So for example, if you want to find a string that is both in A and B, there is no need to build the product. If you guess that string magically, you will not need to build the product automaton itself. And so the question is, can we check equivalence and inclusion without actually building this automata? And this brings me to the last project. Oh man, I'm going really slow. So this is work with Zaki and Kaid. I'll try to give you I don't want to bore you further. But essentially, the idea is I'm going to try to check equivalence of a complex model of automaton that doesn't require to build the automaton itself. So I will introduce you to what are called alternating automata, at least give you the idea. And then I will show you the classic algorithm for checking automata equivalence. And then I will show you the new idea. So symbolic automata, as I say, they have nice operations. And equivalence is using p time for the deterministic automaton and p space for non-deterministic. So this is the same as classic automata. There is this other model called symbolic alternating automata, which is essentially the symbolic extension of alternating automata, where Boolean operations do not cause a blow-up. So computing the conjunction of two automata doesn't cause a giant automata. And equivalence is still in p space. So there is hope that we are not going to die on this. So let me give you the intuition of what alternating automata are by first tell you what non-determinism is. So how do you describe this automaton based on your knowledge of non-deterministic machines?
Both PAQ1 and PAQ2 are in the transition relation?
Yeah, but in terms of what is the semantics? What is the semantics of non-determinism, actually? You guys like the word semantics, so let's see.
Oh, right. Well, at every step, you're at a set of states.
So you have a guess. And whichever works, you're good.
Oh, okay. You can do it that way, too.
So what we call it in logic is disjunction. So basically, I accept AW from P if either I accept from Q1 W or I accept from Q2 W. So it's OR. So maybe we can rewrite this automaton as this. So PA goes to Q1 or Q2. So there is this dual concept in automata which is called universality. So it's from P I accept AW if both of these guys accept W. So we can replace this with an AND. Now we can combine the two and get alternating automata. So alternating automata is just like you can have any Boolean combination of states here. So you can say I accept P A from P if either I accept from both Q1 and Q3 or I accept from, I mean, you can have whatever Boolean combination as long as it's positive over Q. And now the initial state is a Boolean expression itself, like accept from either this or that or this and this. And the final state is a subset of Q like before. And let me just show you how alternating automata don't blow up. So if I want to do the intersection like before of all these BIs, I can just take all their states and just put as initial state, you have to accept P1, and P2, and P3, and P4, and so on. You have to accept from all the initial states. So basically, I just copied the automaton. I didn't combine them. So no exponential blow-up, only 2n. And now let me tell you how to check equivalence of algorithms, and then we'll do some magic. I don't know if I'll get to alternating automata, but at least I want to show you this trick that is super cool. So how do you check equivalence of the automata? Well, you do what is called a bisimulation. So you say, for this automaton to be the same, the languages of their initial states have to be the same. So P0 and Q0, they have to accept the same stuff. For these two to be the same, since they both read A, their successor need to be equivalent. So you just keep going. It's basically a fixed point construction. For any two things that they're equivalent and they can do the same step, their successor has to be equivalent. So this is called by simulation. So as soon as if I find two things that have to be equivalent, but one is final and one is non-final, the equivalence failed. So Hopcroft just does this, but uses this technique called union find to keep set of things that are equivalent, and you get this fancy complexity called n log star n, which is something related to the number of atoms in the universe that nobody cares. Okay, so very fast, almost linear time. And basically, as I said, this is just building what is called by simulation, which is something that is an equivalence relation over the set of states, such that it's consistent. So things that are equivalent, they have the same final state acceptance. And things that step are also in the relation. So if two things are equivalent and they step, their successors are also in the relation. OK, so if you can listen for 5 minutes, then I'll spare you the alternating automata madness. But you really need to see this one, because this is not my algorithm. I did it for alternating. But this guy did it for NFAs, and super kudos to him. This was Popple 2013, one of the best papers, in my opinion, and in many other people's opinion. So the idea is that it turns out that like when you want to do equivalence for NFAs, you can do something really cool. So how do we do Hopcroft-Karp for NFAs, for non-determinism? Well, it's the same as before. I know if P0 and Q0 are equivalent, and I read A, then P1 or P2 has to be equivalent of Q1 or Q2. So essentially, I'm building now equivalence relations over more states, over sets of states. And really what I'm doing the subset construction that you do for determinization and running Hopcroft-Karp over them. And the question was, can we do better? Because, I mean, if we do this, we are essentially determinizing the automaton, so we are not doing anything smart. And this guy showed this thing, which was like, whoa, mind-blowing. So let's say that your relation already says that P has to be the same as Q, and S has to be the same as R. So this is already things that you have in your relation that you have to prove. And now you discover a new state that says P or S has to be the same as Q or R. We actually don't need to explore this, because we can prove it using these facts. So P or S equal Q or R, by rule 1, we can replace P with Q. By rule 2, we can replace R with S. And we show that Q or S is that we show that these facts hold by just using axioms that we learned in the previous step of the proof. And so this idea is called computing the congruence closure of what we have up to this point. And essentially, it gives us a very cool way to cut parts of the search space without not needing to explore, because they follow from other facts I have to prove anyway. And all the rule you have is that just like if two things, if X and Y and A and B, then this fact is also true. This is the only axiom you have, essentially. And this can be done efficiently, and the algorithm basically just becomes that whenever two things are already provable from existing facts, you don't explore them. You only explore them when they're not provable. And I did this for alternating automata, but it's like the only thing that changes is that you do both for AND and for OR. Plus, we did it symbolically just to be fancy. But here, computing the congruence closure were expensive. So since we are symbolic people, we use a SAT solver. And let me just show you actually that it works. So we compare it against this tool called Mona. So Mona is a fancy tool for doing automata stuff. And we were basically doing satisfiability for LTL. And all the times we were faster. And Mona many times was actually timing out, and we were not. And let me show you something that perhaps is more up to your taste. So we were trying to prove properties about regular expressions of this form. So we want to check whether the intersection of these regular expressions is equivalent to the intersections of other regular expressions. And we compare against classic technique, and you can see that in many cases, our tool took very little time, while the classic technique will time out. And similarly, the other way around. But actually, it turns out that we time out much fewer times. Like, we could prove more facts that you couldn't prove with existing techniques. And essentially, the cool thing is that the congruence was causing you many times to explore fewer states. So you were cutting the search space by just proving things about it using existing facts. So conclusion, since you're almost dead, So symbolic automata are a versatile and powerful model, blah, blah, blah. Completely subsume classical automata. So remember to trash your book when you go upstairs. And they give a nice separation of concerns, which was the really cool thing. And there is an opportunity for exploiting existing decision procedures that existing algorithms were not using. So these are all the tools. Actually, they're not all. There are some of the tools that use symbolic automata, and they prove various things. There are 2 open source libraries, one in Java, one in .NET, if you want to use it. I have a page that I keep about all the new results about symbolic automata. Lots of people working on it. Last week, we integrated the theory of sequences in Z3 using symbolic automata. So now Z3 can prove things like a list of integers of length 1 cannot be a list of integers of length 2, and other stuff like that. And but, as I say, I also do other things in my life. So the tool, I haven't decided how to pronounce it yet. So we have a tool for learning how to fix common repairs from examples. And I did a bunch of stuff in personalized education, so how to grade students' homework. And doing some stuff in synthesis of network and data and control planes. And then we are trying to prove when programs are racist, because sometimes programs, they take decisions for us, and you don't want that they discriminate against certain types of populations. So we are trying to describe techniques to actually prove that programs do not discriminate. So it's very cool, and that's it. So thank you for your attention. Yes?
It seems like a lot of the queries you're throwing at the stat solver are similar. And so, you can imagine some interplay with the solver to try to exploit this. But I think on your side, it sounds like you're not exploiting this, but you're just leaving it up to the underlying solver, perhaps, to say, I've done a lot of this.
We cache it.
Oh,
we keep the state. Yeah. Okay. Like in most cases. I mean, that's kind of the thing is that the solver, you give us the solver. So the interface of the structure is that all we have is an interface, literally in a programming language interface. That is it has basically the methods of a decidable Boolean algebra. And then you give us the decidable Boolean algebra. So if your solver caches stuff, as Z3 does, then life is great. And you can also cache, like, you already asked me to intersect these 2 predicates before. I don't need to check intersection again. I mean, you can do more at the automaton level, but sometimes it's just, you want to separate really the things.
Are there any more questions for Loris?
Ask a question about anything. Weather.
How do you pronounce that first project?
No.
Let's see. What's a good way? So I can tell you. I can show you the. Can I show the original tool that we build on, and then you decide. So this is the tool that we replaced. Can I? Or is it bad because can you stop the camera?
We'll edit this.
Eventually, I will have to give this talk. So this is the tool that we are replacing, and so ours is better because it doesn't give.
You have to go to readme.
Oh yeah, here. Or yeah. So this is the tool we are replacing. So if you're wondering, yeah. But ours is better. The idea was like no SQL replace SQL. So I haven't. When the paper will get accepted, I will have to think about that.
Okay, let's thank Loris again, and